Now let's talk about link budgets. Although we aren't actually going to manually calculate the link budget, we should understand all of the moving variables associated with a link budget. So here is the mother of all equations for the link budget, where we have that signal to noise ratio per bit, and it's equivalent to a number of variables, like a product of many variables. And what you want to make sure is that it's greater than some signal to noise ratio requirement. Typically, this requirement is 3 decibels, so decibels, the way you can convert decibels are a log 10 operation. So here, let's just do decibels. So if we have a margin of 3 decibels, then what we want to see is a power ratio of about 2. You want your signal to be twice as intense as the noise floor, as the amplitude of your noise. Okay, let's go back. Hopefully that gives you a little bit of intuition as to, right, above 3 decibels, you want this product to be twice as big as this product down here. Now let's break down the variables. We've got all of these variable names. What do they mean? We've got PT, that's the transmitter power on the spacecraft side. And the way that this affects our design is how much power should the spacecraft transmit a signal at. Then we've got some transmitter to antenna line losses. That's going to take away from the effectiveness of sending a signal. So this is going to be some large number. This is going to be some smaller number, probably less than 1. How big should the antennas be? That's going to affect your transmit antenna gain. We'll see in the next lecture that different antennas have different gain patterns, different power intensities that the antennas can transmit at. So that's what that means. And then we also have to take into consideration free space loss, which isn't explicitly labeled here, but it's lambda squared over 4 pi r squared. This is associated with the power that diminishes as you traverse space. Another thing is transmission path loss, which is over here. The way that this affects the design is different radio frequencies have different attenuations across the atmosphere. So that's how you would embed that amount of attenuation into this link budget equation. And then for our system, you think, how much noise can we accept on the receiver? And you can embed this number into the receiver antenna gain. And then you think about your communication subsystem thermal operating range. What temperature should we keep the system at? And this affects the amount of system noise that goes into the communication, into that KT. So hopefully this helps you envision why the link budget equation is important, first of all, and how we toggle physical spacecraft characteristics or mission characteristics to change the link budget. Okay, so let's dig further into maybe some of the math. So we're talking about the transmitter power and the gain of the antenna. With these two variables, you can get something called the power flux density. which is WT, and that's the power at distance R. This is the power that of the signal you would experience at some distance away. Another intermediate product is the effect of atmosphere and circuit losses. Across the entire signal path, there are going to be a compounding of losses, where there's the free space loss, there's the atmosphere loss, and there are just general circuit losses. And these numbers are going to reduce the signal to noise ratio margin. Another intermediate product is the receiver power, where it's very similar to the power flux density equation. Yeah, I guess it's like power flux densities times some effective area, where your effective area is associated with your receiver gain. Another intermediate product we should be aware of is the energy per bit at perception, which is the receiver power over the spectral something of each bit. And then, yep, here we also have NO, noise. That's equal to system noise temperatures times the Boltzmann's constant. Hopefully these intermediate products give you some kind of intuition as to they should have intuitive values for you. They're packaged in values that you should be able to wrap your head around more than, I don't know, these single variables. I'm trying to explain it in as many ways as possible because I'm not a communications engineer, so hopefully one explanation will get to you. So I'm sorry if it's not a great explanation. Okay. Anyway, now I'm gonna break into the definition of some of these terms. So let's start with antenna gain. In electromagnetics, an antenna's power gain, or simply gain, is a key performance number which combines the antenna's directivity and electrical efficiency. In a transmitting antenna, the gain describes how well the antenna converts input power into radio waves headed in a specific direction. Here, I've got a graphical depiction of what gain can be for different types of antennas. So an isotropic antenna, which doesn't care about the direction at all, the gain pattern would be uniform across all directions, whereas a high gain antenna cares a lot about the directivity of the antenna. So it will have a high power intensity in one single direction, and then you'll see across all the other angles, there's pretty much no power intensity of the signal going in those directions. Okay, so the gain number can be broken down into variables relating to the antenna itself. There's eta, which is the efficiency of the antenna. It's essentially how much power is going out relative to the amount of power that you fed into the antenna. Fun fact, communication subsystems are very power hungry, and they can get very hot because there is some power loss associated with transmitting through an antenna. So if you have a very high eta, maybe you don't accrue as much thermal dissipation. If you have a very low eta, you're going to have a lot of heat buildup in your system, which is why you need to cool your communication subsystem. And then we've got some constants for pi. The wavelength of the signal is important when you're calculating the gain. So is the aperture area of your antenna and the directivity associated with the transmitter or receiver. And then here's the mother of all equations for link budget. this antenna gain is relevant for both the transmitting side and the receiving side of the antenna. So I just wanted to highlight here, that's where it goes into the larger picture. Okay, so there's a concept called equivalent isotropic radiated power. It is a primary design parameter on the transmitter side. So again, you see this gain pattern. This gain, or this value, is calculated by the output power of the transmitter minus the cable loss plus the antenna gain. It's the product of transmitted power and the gain of the transmitting antenna. It's supposed to show you performance at a specific point. Yes, that's all I want to say about that. And you can see it in the mother of all equations. Okay, free space loss. So free space loss is the drop in intensity of your signal with respect to distance. So you can see our signal is embedded into that lambda squared, and then our distance is embedded into that r squared. And the only concept that you should get from this is that a signal's power diminishes with r squared. So the farther you go out into the solar system, the less powerful the reception of the signal is, and maybe the more powerful you have to transmit at. Okay, another term is this atmospheric attenuation term, which is encapsulated into LA in this larger equation. And this affects the way that we choose frequencies. So here is just a general table of the pros and cons of using higher or lower frequencies, where I'm going to get to that in a little bit because this is not intuitive right now, but okay, let's just look at atmospheric opacity. So our atmosphere is an obstacle for radio waves that are trying to get through from space to a ground station. So from gamma ray, X-ray, and ultraviolet, there is 100% opacity or near 100%. That's why we're protected from a lot of cosmic radiation. There is visible light that gets in, but then when it comes to most infrared, also blocked quite a bit. And now you'll see this drop off for radio waves. A lot can get through to Earth, which is why we send in radio. But let's say that we are looking in this band. If we're looking in this band, we're going to see some profile like this, where there is some partial attenuation from the atmosphere due to oxygen scattering our signal, or light rain or heavy rain, carbon dioxide, fog. And there was a question about loss when snow. So in the textbook, I said that snow has no effect, but it does have an effect. That was a mistake in the textbook. It has less of an effect than rain. The intuition behind that is that rain is much denser, and so the scattering will be much more, whereas snow is less dense and will have less of an effect. Oh, actually, okay, good. This does make sense. So higher frequency signals, as you see here, if you go up in frequency, there's much more attenuation. I was, for some reason, thinking about wavelength, which are inverse. So lower frequencies will get through the atmosphere more. High frequency signals will get through free space loss and transmit more data. Lower frequency has less cost and complexity in the electronics, but high frequency can reduce the size of the antenna and also has advantages when it comes to antenna gain. Okay. We only have a few terms left. There's noise, which is that KT term. And I wanted to show you all the places that noise can show up in like the path of a signal. So TX is transmitting, RX receiving. We already talked about the free space loss and the other kind of losses that can happen. But there can be noise as well when it comes to natural noise, antenna noise. There can be noise from generated in the RX, noise generated from feeder loss. So there are a lot of places where noise can enter a system. And one of them is system noise temperature, which I think it encapsulates some of these other sources of noise. What is the best strategy for us to reduce the noise with the current constraints that we have? To reduce the noise, you could reduce the temperature of your system. But other than that, there's two things you can do. You can reduce noise, which is what this question is asking, or you can amplify the actual signal. So amplifying the actual signal seems a lot more straightforward. You pick an antenna with a better gain pattern, you transmit at a higher power, and then there are other like modulation schemes that you could also go after. But reducing noise can be hard. Maybe you can also choose an antenna with less noise built into the electronics. But I think the big picture answer for this question should be, what is the best strategy? It's to reduce noise or amplify the actual signal. Okay, there was another question about solar noise. When traveling to undiscovered bodies in the solar system, is there a way to account for the foreseen noise? Yeah, you can have things called filters. If you know what frequency the noise is going to perturb your actual signal, then you can have filters that reject that noise. But that's only if that frequency is distinct and far away from the actual signal that you want to measure. But let's say that your sun or solar noise is at the same frequency as your observed signal of interest. I don't know what you can really do about that other than post-processing. You like get that data regardless, and then using models or simulations, try and distinguish what of that total signal is noise. Interesting question, but not much you can do if you don't know the frequency of the noise signal. Okay, second to last slide. How do you close a link budget? Great question. Okay, so let's return to this large equation where the goal is to get some ratio above 3 decibels, so above 2. The general process is that you calculate your signal to noise, it's bit energy to noise. Yeah, bit energy to noise with the current design parameters. So you collect all of these parameters, given that you've designed your spacecraft and your mission. So you should know what power you're transmitting at. You should know, given your hardware selection, what the gain of your antenna and receiver are. Given your frequency, you should know what your atmospheric attenuation is. Given your circuitry, you should know what your losses are. Given your orbit, you should know what your R is. Given thermal analysis, you should know what T is. So all of those parameters go into calculating what bit energy to noise is. You check if that bit energy to noise ratio is less than 3. You toggle the design parameters, any one of those, and then recalculate what that ratio is. If you do have a bit energy to noise ratio that's greater than 3 decibels, then the link has closed, and theoretically, you should be able to guarantee a communication link between the transmitter and the receiver. And also the other way around. You also want to make sure your receiver to, there are 2 directions, right? Spacecraft to ground station. You want to make sure that link closes, and you want to make sure ground station to spacecraft also closes. Okay, the frequencies that are typically used for various space missions are, can satellites use the same frequencies and not conflict with each other? That doesn't sound good. I mean, maybe if your satellites were distinctly positioned far away, they would not conflict with each other. But if they were close together and transmitting at the same time, they would absolutely conflict with each other. The ground station may not be able to distinguish the 2 signals apart. Are there few enough satellites that can all find unique enough frequencies within the spectrums presented? So there's an assumption here that's absolutely correct, that there's potentially a finite number of frequencies that can be transmitted in the air at any one time. But as you know, the frequency spectrum is continuous. So you could theoretically transmit at like 420.1 and 420.2 hertz. But the limitation there is that I don't think our technology is good enough to distinguish between very fine differences in frequency just yet. So we could approach like an infinite amount of transmittable frequencies, but we're really limited by the technology that's interpreting and receiving that data, and also the technology that's transmitting. Can you actually transmit at 420.1 differently enough than 420.2? Like, what is the precision of the carrier so that you can distinguish between the 2? That is just like a big answer, the big picture answer, because I'm not a communications engineer. There's probably a lot more nuance to that. Hopefully that's good enough. Is our satellite going to use one band or all of them? Does it really just depend on what our mission is? I think we're going to use the amateur bands, so UHF. But as this question insinuated, there can only be so many satellites in that band at one time. So we're going to have to apply with some kind of frequency coordinator. Okay, done with class.